All right, let's start. So just a reminder, if you join in Zoom from online, I won't be able to see your chat. So if you have any question, say in the webcam or some, speak to the microphone or something. All right. The way we're lecturing right now, I won't see your chat. All right. So any questions about anything? All right. So let's continue with where we were last time. So we were still kind of talking about Brownian motion. We're getting used to Brownian motion and its properties, right? So WT, right, for T negative is a Brownian motion, right? If so, first, right, it's not super important that it starts at 0, but conventionally we do so. Second, right, it has IID increments. Sorry, give me a moment. Okay, and then the third, right, is that we need to say what the increment, what distribution the increment has. And so here, right, it has normal distribution. Now, by the way, right, later on we'll talk about Poisson process that will incorporate jump, okay, into our Black-Scholes model. And you'll see that the Poisson process has almost exactly the same structure, except that instead of normal distribution here, we'll have a Poisson distribution. So this kind of like, description of a process is super, super nice. Unfortunately, it only works, right, for Brownian motion and Poisson process, but those are kind of like two prime examples, right, for stochastic processes when you first learn, how to deal with them. And also they're used a lot in, modeling, right, at least at the basic levels. So it's worth it to kind of get used to the structure and kind of know how to manipulate them. All right, and so we discussed, right, how to play around with these properties last time, so I won't repeat the details. But some of the thing, right, that would be important to note, right, is the following. Something, right, kind of nice, right, to keep in mind. So first of all, right, this property that the increment is always dependent of the whole past history, right, is important. Yes. So basically it says that once if you know the past history, right, and this filtration means that you have all the information from time 0 to time s. That history of the path, right, what it says is basically, now that you've seen Brownian motion path as well, right, so here's S. Basically, you could, right, observe the path up to this moment, okay? That won't tell you anything about how high or how low the Brownian motion will be, oops, sorry, right, at time t, okay? So whether the Brownian motion is here, wherever, right? So this whole increment will not be, right, deducible, or you have no knowledge of saying what this will look like given the whole past history, right? That's the most important thing about Brownian motion that we got out of this. Conversely, right, do remember that WT minus WS is not, right, independent of WT. In other words, right, conversely, if you know the future, right, if you know this point, then in some way, right, it has some correlation with the past movement, right? So you're right. The other way doesn't work. So that's the flow of time, right, that we need to pay attention to. Okay. I guess out of this, right, also it says that WS and WT are not, right, independent. So our motion, right, which is random walk, is correlated, right, among themselves. Okay. The IID structure that you think about is white noise, which is the time steps, okay, of the Brownian motion, not the Brownian motion itself. Okay, so these are usually the things that I kind of remember Brownian motion. Now that said, right, all these will allow us to say definitively about the joint distribution of the Brownian motion like this. Remember, I said, right, for any process, what you really want is the joint distribution, okay, of any collection of the value of that process at any time, right? This is called the finite dimensional distribution. As long if you have a way to say for any collection of t's, right, how this looks like, the joint density of this, then you're done. And I claim that, right, for Brownian motion, knowing this description is the same as knowing this, right? Now that we have done enough calculation, I can tell you, right, what this looks like is actually just a normal. In fact, it's a multivariate normal distribution. So for multivariate normal distribution, right, you need two objects, the vector of the mean and the covariance matrix, right? So this is multivariate normal. So here, right, mu obviously is just a vector of zeros because the Brownian motion, right, is centered at 0. It's the covariance matrix, right, that is important. But here the covariance matrix is, so on the diagonal, right, it's just T1, T2, up to Tn, right? And on the off diagonal, which is the covariance, right, we'll just say something like this, right? The minimum of Ti, Tj. Okay, because we don't assume that these T's, are increasing. If they're increasing, then, you can feel it even more easily, right? But basically, this is the covariance matrix of the, right, Brownian motion, finite dimensional distribution. So that, right, completely describes Brownian motion joint distribution for you. Okay. Any question? By the way, right, the multivariate normal is a very important object that you should learn by yourself. It shows up in many, many places, right? Here is pretty simple, so we'll just mention it casually. Okay, so now let's go to the real, right, the substance of this kind of structure, which is calculus, right, with Brownian motion, which is, kind of what we mean by stochastic calculus. By the way, so basically what I try to say is doing calculus with Brownian motion is part of stochastic calculus, all right? I mean, I don't mean that stochastic calculus is just about calculus with Brownian motion. It's much more, right? In fact, any calculus, right, that has to do with random processes will be stochastic calculus. But here, right, we'll focus on doing calculus with Brownian motion only, okay? And we'll expand to horizontal process, as I said, in the future. So what do we mean by calculus with Brownian motion, right? So first of all, let's say something pretty obvious, that W, right, is a function of T. Okay. Now, so this is worth saying a little bit. So when you're given a stochastic process, okay, it's actually a function of two variables. First is a function of time, and second is a function of event, which is usually hidden, right? We don't say it. So when you fix a time, right, then you look at WT itself as a random variable. And that's what we've been doing above, right? We kind of fix some time and we look at this as random variables, okay? And we can discuss the properties. Now, the point of calculus is actually the opposite, that you kind of want to fix an event, okay? And look at W as a path, as a function of time, okay? And this will bring in a lot of trouble, as you will see. Because, right, so actually, right, also we've been exhibiting this for you, that, so this is a fix an event, right, and see a path. So WT now is a path. W, right, is a function of T is a path, okay, or a function of T. So basically, right, I think is kind of very trivial. Every time you run the simulation, right, you get a different path, right? And that's what we mean by fix an event, fix an omega. So again, right, calculus is kind of dealing with this aspect as a function of time, rather, right? So probability is dealing with the function of, right, omega as a random variable. Calculus, right, deals with this aspect. And of course, together, right, is stochastic calculus. We look at both at the same time. All right, so why is this important, right? Or why do we care about this, at least in finance, right, or whatever? So remember, right, so I guess for us, right now, what's important is I want to, again, convince you on the connection of these objects. So first of all, right, I call this the differential description. Right, of the Black-Scholes model. Okay. Now, of course, right, I spent some time trying to explain to you that it might look strange this way, but if you try to divide by ST, then it's just a model, right, for the percentage return. So hopefully there's nothing strange, right, from that point of view. But we will not look at this from a mathematical point of view, all right, as you'll see. Because from a mathematical point of view or from a calculus point of view, it's much easier. And actually, we must work with, right, the differential or the change in the stock price. This guy is not a differential, as you will see, right? It's not a change of anything. On the other hand, right, we also have the log return, which is much easier to understand, like this. Okay. Oh, sorry, there's a ST there. Oh no, that's it. Yep. So there, right? Here, right, this is the log return. Why? Because this is, right, log of ST plus DT minus log of ST, which is, right, exactly log of the ratio. So that's the financial meaning, right? On the other hand, from a mathematical point of view, this is also a differential description of the Black-Scholes model, but it's not differential of the stock, but it's a differential of the log price, right? So this is also a differential description, but differential of the stock price, right? Of the log of the stock price, of the log price. Okay. And finally, right, we have the model itself, the explicit model. Right, so this is, of course, right, the explicit formula. Okay, so the point of calculus, right, is to show you that 1, 2, and 3 are one and the same description, right? And in fact, the homework of this week asks you to check that out a little bit. In other words, right, using, simulation, right, I asked you to simulate a path of the stock price using this description and simulate the same path, I mean, using the same data, right, simulate this path. And if these two descriptions are exactly the same, then of course, right? I mean, so sorry, if you plot these two paths and you see that they're similar, that they're almost the same, that means that these two descriptions, right, mathematically talk about the same object. Okay, so in case you kind of find this, right, a little bit overwhelming because, you know, it has DW kind of thing, this is exactly, right, similar to something like this. Right, in calculus, you might have something like this. So this is the derivative, right, of a function. You call this f prime. Notice this is just a notation, right? It just say that, well, the different derivative of a function is some other function. Now, if I were to ask you how to differentiate log, what would you do? This is a calculus question, right? If the derivative of a function is f prime, what's the derivative of the log?
1/4x.
Yes. That's it? Correct. All right. So in other words, right, these two would be equal. And also, right, another one is you guys would have no problem agreeing that these three are the same, one and the same thing, right? They all describe the same object. Yes. Now notice, right? Let me just rewrite the first two. The first one, maybe you have never seen it like this, but it could. The second, and then of course the third, right? Now, why do I write it the first two like this? Because now, right, it looks like the differential formulation of the stock price that I wrote above. You see? So ignoring, if sigma is equal to 0, then exactly we go back to the differential that we looked at before. Right? So in fact, what we're doing is an extension of classical calculus, but with this funny looking guy right here, right? The Brownian motion. And that's why, right? So classic calculus is calculus with Brownian motion, because it's this guy that's going to cause us some issue that we need to study. Right? Questions so far? So the point is, do you understand why what we're discussing, right, is an extension of classical calculus? Notice also, right? Maybe you haven't noticed this, or maybe it's very natural. What is this trying to say? This is trying to say that, right, a small change of the function is whatever that derivative function is times a small change in time. Right? That's all that's trying to say. Now, if you use that, you know, calculus 101 formula that I was saying, which is for any, right, any function, when you add the change, you get back the big change, right? Remember this telescoping idea, right? This is calculus 101. It works for Brownian motion, it works for stock, it works for anything, right? I said this before too. Right, remember? So, right, this is just adding a small change, giving you the big change. However, right, because we claim that we know a small change of the function can be matched by a derivative times a small change in time. Therefore, this is the integral as you know it, which is this. All right. And then of course, this is just, you know, derivative, you know, chain rule, right? That's what you're saying. But kind of pay attention to, right? we don't say it out loud when we teach calculus, but essentially what calculus does is kind of transferring the change of the function itself into a change in time. So you want to, right, because the function is a function of time itself or some independent variable. To describe the change of the function, you want to match it with the change in the independent variable itself, which is time. So you want to track the change of the function with the change in time. All right, that's what you want. That's what you're doing here. You are recovering the function with action in time only. Now we cannot do this. I mean, or not that we can do this. We cannot do this. But with stochastic model, there's a change in time. Right. By the way, this is time value of the growth of the stock, kind of, right? This is like a stock deterministic growth. If there's no market influence, then the stock would grow in its happy way with the rate mu. Right? The whole point of the stock is that it has stochastic action, trading, right? Makes it go up and down, fluctuation. Therefore, right, a movement in the stock is no longer now can no longer be just tracked with the movement in time, but also with the change in the noise, right? The noise part, which is prime motion. So incorporate this and how to track, how to recover, right, the stock is the point of stochastic calculus. All right. Any question? So again, all of these are trying to kind of get you into the frame of mind on knowing, right, what we're doing with stochastic calculus and why we do it. So let me tell you, right, that stochastic calculus is something new, all right? So by instead of saying new, I say something strange. But what it means is a new object. It's not, you cannot. So basically, what I'm trying to convince you is your regular, right, calculus, your classical. So by the way, right. So from now on, when we do this kind of thing, we'll say classical calculus, all right, meaning calculus without prime motion. So I'm trying to tell you that your rule of classical calculus doesn't directly translate, okay, to the stochastic framework. Here's a demonstration, right? So suppose that, so again, right, I'm rewriting the two model. So it's just a relation of the percentage return and stock and log return. Remember, I told you that pay extra attention to the fact that the log return is lower, yes, than percentage return. And you saw with data and everything, right? So that's kind of all cool and good. Except that notice that it's not that trivial to achieve this effect. Sigma has to be non-zero for this to happen, right? So let me say this, right? Suppose that of course, if sigma is equal to 0, then there's nothing here. So that's good. But let me just kind of be a little bit weird. And let's say that somehow I just drop the prime motion itself like this. Right? So I just dropped the prime motion, okay? Now, if this is the case, then what is d log st? Using classical calculus rule. Well, maybe you're not used to, right, asking the question in this way, but actually notice, right? So here I was trying to let sigma equal to 0. Pretend that you don't know this, all right? So this is this, right? With f prime equals to mu times st. See it? Right? This is this with, so f is s, right? F prime is mu times s, right? So these two are actually exactly the same. Okay? So d log will be f prime, right? Which is mu st divided by st dt. Agree? according to exactly this is calculus. I mean, if you feel it's strange, again, you can derive by dt. Because here we don't have the right motion part, right? I assume sigma equal to 0. Okay? So in other words, if you were to follow classical calculus, then d log st must be just mu dt. Agree? So in other words, right, this minus 1/2 sigma squared is entirely due to the Brownian motion. Somehow, right, because of the presence of the trading of the volatility, that when you calculate the log returns, it pulls the average return rate of the log lower. Okay, so that's what I mean by something, I hope, well, strange, dramatic, right? Something new. In other words, right, there's something worth studying about this. There's a new thing, right? Without the action of trading, then the rate of return, whether it's percentage or log, is exactly the same. Okay, without any volatility, then by this exact calculation, we say that the average rate of return is the same. Meaning, if the stock is deterministic, then it doesn't matter how you calculate, it's the same thing, right? Why? Because actually here, right, there's no distinguish between percentage return anymore. Both of the case correspond to exponential growth. Sorry, ST equals to, right? So when sigma equal to 0, this goes back to your saving account, which saving rate means. Okay. So there, this sigma, right, or this component is what, make the average rate of return of the log to be lower and all those kind of things, right? That's what we want to understand and develop. Okay, so this is just classical calculus. Any question? All right, so now having right kind of show you where we're going, the next step is what we need to learn how to integrate with prime motion. That's the first step to understand all these things. Okay. So even though it seems like what we're dealing with is derivative, differential, the first thing we want to learn is integrating. In other words, right, what are we doing? So the goal here is that given, right, a Brownian motion, okay, and another process, well, let's call it, delta t or something. All right, I will not say much about this process. It can be almost anything. In Math Finance 1, Professor Larson would tell you that this has to be adapted, with a filtration WT, that kind of thing, if you want. Let's not be too formal about that, which is fine. So basically, some adapted, measurable process. Don't worry about that. Then what I want to do is we want to make sense out of the integral delta u dw. All right. And let's call this v if you want. Okay. So let's pause a little bit and see what we're doing here, right? First of all, right, so w is a stochastic process, all right? Delta is yet another process. What I'm doing here, right, is like I'm integrating with respect to the Brownian motion. And that's why, right, it has that name. Now, in terms of meaning, right, what am I doing? So approximately what I'm doing is I'm summing like this, right? Where, again, the picture is I have, right, time interval like this. I divide it, right, into many sub-intervals. So this is T0, T1, T2, right, up to Tn, right? And then, so this is just the Riemann sum. And then you push the delta t to 0, right? You take the limit. So this is like the Riemann sum, right? And this is what exactly this is what you do in your numerical, right? In your simulation to get to the stock process, right? And the prime motion process. Okay. So when you do this, right, you get, so first of all, mathematically, when you do this, you get a new stochastic process, all right? So let me say that right away too. So you get a new process, new stochastic process. So basically integrating with prime motion, right, gives you a new process. Now, so what's the big deal, right? I mean, well, you just take the grid point, right, do this and take the limit. The trouble, right, is exactly in this step right here. Taking the limit in the traditional sense won't work. A lot of strange things will happen when you take the limit, okay? Now, when you, I guess you're used to, I don't know, like you're used to, right? The integral, let's say, of some function, right? So, oh, by the way, right, I'm not sure the word delta makes you feel strange. Delta doesn't mean change. Delta is just a process. So let me change it to something else. Maybe delta suggests to something weird because we might use delta as change here. So let me change it to phi, all right? So you're used to something like this, phi of u du, right, which is the limit of the sum, right? All right. So in fact, you do this a lot, right? This is how you kind of compute like numerical integration, right? So, but if you ever took any kind of analysis course, right, undergraduate or something, you see that actually people spend a lot of time proving that this actually converges. All right, this Riemann sum actually converges. And so this, first of all, takes some time to establish. Now, the second thing I want you to pay attention to is here you're taking the limit as time, right, goes to 0. Here, when you push time goes to 0, what you're adding is you're adding the change of the prime motion. Okay. And in fact, as we'll see later, this depends on the regularity of the prime motion path. Okay, I'll explain. But roughly speaking, I think you can already see why, right? Because prime motion, here's a change of prime motion, right? You're pushing time to 0. So it depends on how well behaved, right? The change of prime motion with respect to a change of time. But needless to say that, right, the prime motion itself is very, very, very rough, right? The path of prime motion is very, very rough. So when you push time to 0, the change in the prime motion becomes very, very wild. The key word is nowhere differentiable, okay? The prime motion path is nowhere differentiable. So you run into the trouble when you take the limit as delta t goes to 0. Okay, so that's the mathematical part of it. All right, so understand this much right now, right? That we're looking, right, to make sense out of integrating with prime motion. Integrating with prime motion is routinely just a Riemann sum, all right? Where the integrand, right, where the integrand is some process and the integrator is the prime motion. So we're adding the value of the integrand against the change, right, of the prime motion and add those up and take the limit, right, as time goes to 0. Now, if we successfully could carry out this process, or we could make sense out of this, procedure, then we will obtain a new process. All right. But as I pointed out, this process mathematically is very, very challenging, and actually you cannot do it straightforwardly because prime motion is very, very rough. All right, it's nowhere differentiable. Unlike, right, time itself, right? When you push time to 0, actually, right, time behaves very nicely. So in fact, there's nothing to talk about here. But of course, right, even in this case, you did spend some time in a classical calculus course or classical analysis course to show that this actually converges, right? So even this takes some time, but we kind of take it for granted for now, right? And focus on this. Any question? So now I want to spend a few minutes talking about the financial, right? Or the meaning of this. Why do we care about integrating with ground motion in all this context, right? Or meaning of integrating. Of stochastic integration. All right. So like we were spending time talking about, right? So I guess I want to say this. Above, right, I was trying to sell you the differential, right? The differential version of the stock, meaning I was trying to sell you that, right, we're describing the small change in stock price, right? We're describing small change in stock price, small change in lot price, etc., or the stock price itself. And then suddenly down here, I was talking about integration, right? Meaning adding up things. What's the connection? Now, I mean, if you have taken calculus and you kind of understood what's all about, then maybe you'll see what I'm doing here. Integrating and differentiating are just two sides of the same coin. All right. I mean, you integrate and you reverse it, right? You differentiate, right? In fact, you can kind of see it right here too already, right? Right here. This, and this are one and the same thing. This is the integrating version of things. This is the derivative version of things, right? But now that you're used to it, you say they are the same. But see, once you have the derivative, then you integrate the derivative to recover the function. If you have the integration, then you differentiate to figure out the derivative or the differential change, right? So these are two sides of the same coin. So that's the same thing here too, right? That when you have, let's take this, right? When you have the differential model of the stock, let's say naively you want to recover the stock, what would you do? Naively, if you want to recover the stock, then you should be able to do this. Okay. Now, so right here again, I'm using that integration 101 formula that is always true, right? Universally true. To find the big change of the stock or whatever process, I'm just adding, right, the small changes. There's nothing here. Right? This is a truism. This is always true. But the next step, when I plug into the what the change is supposed to be, then I encounter, right? It's actually two pieces. Okay, so far. Right. So what I'm trying to say here is if I accept the differential, right, model of the stock, which is a percentage return, then if I want to recover the stock price naively, right? Because why do I say naively? Because I don't know what asset to begin with. But I'm just suppose that everything here goes through, right? And I'm just doing the math. Then you see that, right? In recovering the stock, right? You have to deal with two objects. The first one is the regular Riemann integration, where you move, right, when you add the stock effect with respect to time. But the second object is exactly that new guy right there. This one is exactly the integrating with ground motion piece that I was talking about, where phi here is sigma times s. All right. So in recovering the stock price, I will have to understand how integrating with ground motion works. So that's one thing. All right. The second one is probably more, more meaningful. The second one is when you construct a portfolio, all right? If you have a portfolio, let's say in stock, okay? And suppose that at any time you hold, and here's where the word delta comes in. Somehow it's traditional to use delta to denote the number of shares. All right. And you suppose that this portfolio is self-financing, meaning that you don't insert money in and you don't take money out of the portfolio. We'll talk about that later. But basically, what self-financing means is this, right? So let me say this, right? Suppose that, so let's call the portfolio value V, okay? Let VT be the value of portfolio time T. Okay. So here's a question, how is V connected to stock and the shares? And by the way, right, this can now change, right? Delta now is a function of time, so it's not buy and hold. You can dynamically, right, trade, sell stock, buy stock, whatever. The catch is that it must be self-financing. And let's talk about what self-financing means, right? So self-financing has this meaning. Suppose you take two time moments, right? Let's say this is TI, this is TI plus 1, right? So this is a value portfolio time TI, value portfolio time TI plus 1, all right? Now, so the change, right, in your portfolio value from this time period is this quantity, right? VTI plus 1 minus VTI. This is a change in portfolio value. Now, what could cause a change in your portfolio? Well, because we assume it's self-financing, you're not taking money in, you're not moving money out. The only change that can happen is because of the market movement, meaning it can only come from the change in stock price. In other words, right, it just however many shares you hold at the beginning of the period, right, times the change in the market movement. Is that okay? This is the meaning of self-financing. With me? Any question? Now, and then we'll do this a lot, all right? And we'll be a little bit casual about this. But if I push time to 0, right? Of course, because we're trying to model continuous, right, action here, continuous trading, right? Whatever that means. When you push time to 0, right? So this is a change, right? When you push to 0, then the change becomes the differential. It's just formal, right? There's nothing here. So what I'm trying to say is, when in the infinitesimal sense, this is what I'm trying to do, right? A small change in portfolio value is the number of shares you hold at that time times a small change in stock price, which is exactly just the blown up version of this. Okay. However, right now, if I use the stochastic calculus or the integration truism, right, that I wrote here, what do I have? If I want to recover the portfolio value itself, right, like this. First of all, the truism told me that I'm just adding the small change, right? However, right, because of self-financing, I know how to track this small change in terms of my portfolio composition. All right. Again, I want to pause and note that, right? I use T here because there's no integration. But when I have a definite time, right, terminal time, I need to use U, right, to denote the integrating variable, right? It's a bit annoying, but pay attention to that, right? If U here is like a dummy variable, right? If you change it to T, then that makes no sense because that's like you're implying this is not changing or something because T is a constant here, all right? Small thing, but just pay attention. But now, right, what is this? if you are assuming Black-Scholes model, then, right, you see that you're encountering exactly two objects. In other words, oh, sorry, delta U, right? Okay, so to track the portfolio change, there are two actions, there are two objects you have to understand mathematically. The first one is the classical Riemann integration. Here you just integrate, right? Portfolio holding, stock price against time. This is fine. But the second object is much more troublesome, right? Portfolio holding, stock price, but with a change in the brand motion. So there, you encounter this stochastic integral again. Any question? All right. So now you see, right? It really, right? The brand motion keeps showing up is exactly because our model itself, right, incorporates brand motion as the noise, as a noisy source for the stock, right? If there's no such thing, then everything goes back to classical calculus, and we have nothing to do, right? Exactly because the stock itself incorporates a brand motion component. That's where, right, everything comes from. That's where, right, the source of things is to understand integrating with respect to brand motion. All right, so that's a new thing. The final thing, any questions so far? The final thing I want to mention, right, is, so the first one is completely theoretical, I guess, but it's important. The second one, right, is portfolio tracking. The third one is sort of about delta tracking, or the Greeks, right? So when you price a portfolio, when you price an option, right? When you price an option, I think before, right, I wrote something like this. Let's assume it's European, all right? So at the expiration, right, you have some description about it. And the point of pricing the option is that at any time, right? So now let me write it as this, little v, TST, all right? So before I wrote psi, right? But I was just trying to explain things to you. But, right, so the pricing of the option is that at time t, right, this function is given because that's from the contract. Your task, right, is to come up with this description, right? So the task, right, is to find v, right, as a emphasis, right, deterministic, right, function of t and st, right? If you have any doubt about this, think Black-Scholes formula. I think we wrote it too many times. I will not, bore you with writing that one more time. But if you have any doubt about what I'm referring to, just think Black-Scholes, right? So now, obviously, right? Not obviously. There are two ways to approach this. One way is to use integration, right? To use probability, right? Like you did in your homework. Use probability to calculate that conditional expectation. Another way is so the first approach, right, is probabilistic. Which is taking expectation. All right, and you do your density argument, whatever, right? And you saw that on the homework, which is fine. The second approach, and by the way, the probabilistic approach may not always work if this option is very complicated, or if the model is complicated, you actually don't know what to do either. The second approach is actually the PD approach, or the differential approach. By the way, right, the word PDE here, and the reason why you guys are asked to kind of know a little bit of PDE when you sign up for the program is because of these kind of things. But I just want to tell you that PDE doesn't have to be too abstract or anything like that. Think of the Greeks, all right? By Greeks here, right? If you have known it, great. If you have not, it's about the derivative of the option with respect to different parameters, like the delta, the gamma, right? The vega, that kind of thing. But what is the PD approach? Or we're not going to say it right now, but I just want to describe, right? The PD approach actually is very, very natural too. It's like this, right? You want to understand the option price, right? Okay, fine. I'm not going to understand it this way because, right, it's too complicated. What I'll do is ask this question, right? Again, the question is, here's time t, right? Here's time ti plus 1. Can I understand how my option has moved in terms of value from here to here? All right. In other words, how does the option move? Notice it's exactly a very similar question to number 2, right? Except here we deal with portfolio, here we deal with option. But you will see that, right? It's the same thing. In other words, right? VTI plus 1 minus VTI, right? Must be equal to, because now we assume, right? Or not we assume, the whole point of pricing is that the option value is a deterministic function. We don't know what that is, maybe, but we can still represent it abstractly as the letter V, right? Of T and ST. In other words, I can still plug in. Yes. Now, here is where you kind of start to use your calculus, because you think, right, well, if right, the Ti and Ti plus 1 are close, then the change in this function from a pure calculus point of view must be, and then here I'm not being precise, right? We'll revisit this later. Must be something like the differential, sorry, the partial with respect to T of V times the change in time, plus the partial with respect to X times the change in the stock price. And maybe some higher order terms. All right, this is nothing but a piece of calculus 3, right? A change of a function of 2 variables is what? The partial with respect to the first variable times the change of the first variable. The partial with respect to the second variable times the change in the second variable. Now, the dot 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 here will be meaningful later, as you will see. But the point is this, right? You see that even at this level, by the way, this is called the theta, like the Greek theta, right? Because this is the change of the option with respect to time. Not technically speaking, theta is changed with respect to the expiration day, so it's probably minus theta, the expiration, right? But this is exactly your delta, the delta of the option. Okay, so it's just saying something very natural. To track the option change in value, you track the option change in value with respect to time, and you track the option change in value with respect to stock. Okay, but it turns out that the gamma also plays a role here. That's why dot dot dot. But the reason why I claim, right, this is relevant to stochastic calculus is exactly because, right, you know that this by this claim, you are claiming that you can recover the option value by integrating all these guys up, right? And when you integrate up the stock price, then you exactly, again, under Black-Scholes, you deal with this model. Okay. So to understand, right? So I guess to understand, maybe this is a broader connection between stochastic calculus and option pricing. That option pricing, also, sorry, stochastic calculus allows us to connect option price change with the Greeks. And if you can connect it, right, in the correct way, so using calculus, using stochastic calculus, right, then you can connect all the Greeks together, right, in an equation. That's called the Black-Scholes PD. All right. So maybe I'm a little bit vague on how the connection works, right? But I'm just pointing out that when tracking the change in an option price, it's very natural for you to, right, take the partial derivatives with respect to the parameters, time and stock. But when you, especially when you deal with delta, right, I just want you to understand that this implies exactly that you can recover, right, the option by reintegrating this equation. But when you reintegrate this equation, right, you are dealing with exactly the change in the stock, which is, right, this guy right here, which connects with, right, prime motion. Okay, these things are as abstract as it is first time you see it, so you get used to it. Any question? All right. So now, so these are the application or the things you be performing this action to, right, in the later homework, in the future homework. So now let me discuss about the regularity, right, of Brownian motion. By this, right, I mean regularity with respect to t, right, with respect to time, as a function of time, the path, right, and its connection to stochastic integration. Okay, so the above, right, was just discussing what we mean by stochastic integration, roughly, and why we care, right, in terms of finance and stuff. Now I want to, right, go to the technicality of why, right, that piece is hard to perform. So remember, right, I was saying something like this: the integral of 0 to t, right, of, let's say, phi of u dwu is equal to, in some sense, the limit as delta t goes to 0 of phi ti wti plus 1 minus wti, right? And I said, right, that this sum, when you take the limit, is troublesome, or it's actually very, 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 very strange. The reason is because prime motion, right, is nowhere differentiable. So I want to make that connection, right? So first of all, in terms of regularity, Brownian motion is nowhere differentiable. So Brownian motion path, right? Okay. If you came from the math background, you might have heard of this term before. Have you? A nowhere differentiable function? Maybe, maybe not. So here's what we mean by a nowhere differentiable function. Or here's how weird it is. Try to think of a nowhere differentiable function, or try to imagine a nowhere differentiable function in your mind. Okay? My claim is you cannot. Our human brain is just so wired into think, or your education is so wired into thinking regular functions that you may not even recognize it, right? So for example, let's just say that you think of something like x squared. I'm just giving you an example to show you what this means. sorry, let's do time, right? Because we're doing time. So if you think of something like t squared, then this is a everywhere differentiable function. Because, right, it's perfectly smooth. Now, the next thing, then you say, okay, I know what to do. Let me cause some trouble. Oh, by the way, right, I think I forgot to mention this because it's kind of obvious. It's continuous, right? Meaning it has no gap. All right. The reason is, you can cause some trouble cheaply by doing something like this, right? By having a jump, which is not what we see in prime motion at all, right? You know what I mean? So I want you to this just to be technically, to correct to say that's not the reason. All right. So you want to come up with a continuous function, but no y differential. All right. So the next thing you will do is something like this, right? To have a corner. You remember your education, right? Which is really the absolute value function of t, right? But when you look at this is only non-differentiable at one point, right? Only not differentiable at one point. Only at 0, right? So again, this is nowhere differentiable or everywhere not differentiable, right? So this is perfectly fine over here. So you're like, okay, let me make a lot of corners, right? I don't know. But you see, doesn't matter how many corners you draw, you still only have finitely many corners. So and also actually, what does this remind you of? This should remind you of the binomial model path. Yes, the binomial model path is this and then this and then this. Remember, look at the Python code, right? So then you kind of see what the trick is. The trick is you have to keep dividing this and take some kind of limit action. So in other words, right, even if you want to encounter no y differential function in, let's say, a regular context, you won't. In other words, we can't draw it. There's no way you can draw it. It's a limit, right? It has to be defined through limit. Okay. So that's all I want to say, first of all. In other words, right, that's not some piece that we can just draw by hand. So that comes back to this question, right? Okay, if that's such a complicated object even to obtain, as an example, how in the world do I know that this path is nowhere differentiable? Right? I just want you to appreciate the math, because right up over here, notice that I claim, right, this completely captures prime motion. And it does, trust me, it does. But stare at this for 5 seconds, if you will, and try to see if anything in here says that the prime motion is continuous even. Does anything in here tell you that the path of the prime motion is continuous? Nothing, right? Why? Because this is a point-by-point description, or like an increment description. So it's actually a piece of, I don't know how to say this, a piece of really advanced work to even show that this somehow implies that when you draw the path, it must be something like this. All right. By the way, right, this is where, I like, Python demonstration. It brings everything to your eyes. But the fact that we can draw this in Python and saw that it's continuous, does that prove that the path is continuous? The reason is no, Python automatically connects the dots for you, right? I mean, all Python draw is a bunch of dots, and then it connects the dots, right? So it looks continuous, maybe because Python connects the dots. You understand? That's how Python does, right? When it plots a graph, it just connects. So in fact, right, I mean, I claim to show you some stochastic calculus. In fact, right, we just try to have some intuition. if you want to have a rigorous proof of something like even the Bragg motion path is continuous, that's how it works. All right. So I just want you to appreciate that the definition here, right? To deduce the path property from the definition is some non-trivial work. All right. Nevertheless, right, we are not even satisfied, right, at the level of continuous. We want to go even deeper. We want to show that it's nowhere differentiable. Now, also to show you that we cannot get at this at the Python level, right? Because if you look at Python, right, because Python basically all it does is make a lot of points, right, and connects dots, right? But the segment is too small, so it looks like a lot of corners. If you zoom in far enough, right, then you get to these segments, and these points are differentiable, right? Because I mean these lines, right? So what I'm trying to say is like with Python, you will never get to this thing to begin with. That's a piece of human imagination, if you will, right? Or taking the limits, all right? So, but there is some evidence that we can acquire, right? So what I'm trying to say is, right, you will never, right, observe this with some physical sketching. Right? Because I hope you recognize that everything we do with computer is finite. Even if we push it to a billion, it's still finite. So that's why someone joked, not joke, but there's this philosophical thinking that AI cannot replace human brain because we can always jump to the infinite and AI will never do infinite. Who knows, right? You subscribe to however you want. But basically, right, the reason computers are so powerful these days is it can do a billion things. And with a lot of things we do, when you do a billion things, you already kind of get to the convergence part where the error is so small we don't care, right? But when there's some object like this, that the statement is so abstract, right? Then seeing it with the physical sketching is too simplistic. Nevertheless, there's still something we can do, right? Some other way, right? To see some evidence of this. And this actually brings me back to the connection with the stochastic integration. It's like this. And let me ask you this, right? And this is a strange thing. But so let me go back to classical calculus. And let me take a differentiable function. Take something very smooth. Let's say e to a t or sine of t, whatever, so f prime, right, exists. And then take another, right, function. Let's say g of t. This one can be anything, as long as it's not too bad, all right? I mean, like in terms of regularity, it can be anything. Then my question to you is, can I do this? Does this make sense? So, okay, so maybe anything is too much. Let me say this. This guy, the only thing I require is Riemann integrable. All right, but so G can be discontinuous. It can be this saw function. G can be anything, but I want my F to be smooth. All right, I want my F to be smooth. So, and I want to add, right, G against the change in F. Does that make sense? Can I do it? So concretely, right, let me say something like this. So let me just say something easy. Let me take both to be smooth. Let's say f of t is, let's say, sine of t. G of t, let's say to be e to t. All right, so let's make both of them smooth. What do you think I mean by this? Right now, this is very close to your traditional calculus. What do I mean by this? Well, maybe it's not easy to see, but that's a trick that we can always do. Now, this trick may be frowned upon when you study calculus, but trust me, it's fine and it can be justified. Guess what? I'll do the trick of multiply and divide by d. All right. Well, it is frowned upon because, when you study calculus, people will tell you this makes no sense. So how can you do that? It's not an object. But what really means is that we just, divide it into, small time points like this, right? Sorry, the Riemann sum, right? You do the Riemann sum, and then you divide and multiply, and then you take the limit. It works, all right? So trust me, it works. But when I do this, right, what is this object? I claim you know it. What is it? What is this object? It's not mysterious. It's called cosine. Because this is just the derivative of sine. All right. So actually, this is a what? This is a change of variable. This is a change of variable formula that you always do. Actually, you go the other way. You go the other way, right? Very often, like this. Sometimes you do this. Right? And then you call this, sorry, you call u squared x. But you do this so much, you don't even, but you think of it as only symbolically, right? But, it's actually that. So it's a change of variable formula. So this becomes integral from 0 to, t square root of t or something like this, right? But, right, what I'm doing here is just the opposite, right? So, right, but what's the catch? The catch is that when I do this trick, what do I require? I require that this must be differentiable. So I can write some other function in its place. Notice, right, if I were to try this trick on the Brownian motion integration, well, so formally, right, this trick still works, whatever that means. But now when I ask, okay, what's the derivative of the Brownian motion? The answer is does not exist. All right. So by the way, right, this guy actually has a name. This is called the Stooge integral, Stooge integration. Not that the name matters. But what it means is, right, again, it's just adding a function g against the change in the function f. Right? It's very much the same meaning, right? But it's more general than the Brownian motion. Sorry, it's more general than the Riemann integration, because Riemann integration only wants to add against the change of time, identity function. Stooge says that, well, once you understand that, you can add against any change of any function as long as it's regular enough. Why? Because once you have that, I can always cast it back to my Riemann integration. Except, right, that trick, as awesome as it is, it cannot handle our Brownian motion. And so that's the connection I was kind of alluding to, right? Why the regularity hurts when it comes to integration. Because, again, right? And I hope here you see that this is what I was referring to. When you do d of something, right, you're implicitly pushing time to 0. But then you see, right, when you push time to 0, you want the relation between this and this to be nice. And the relation is nice by the existence of the derivative. If the relation is rough, you cannot track, right? Basically, the message is as time goes to 0, you don't know if the Brown motion is shooting up, shooting down, how much is shooting, because it's not differentiable, right? I mean, ultimately, derivative just means that you can control your change when time is small. Try to drive when your speed is not differentiable. You will run into a road, you will run into a tree right away. Because with a small change of time, your curve is not smooth, right? So that's actually what happens with Brown motion. We're trying to somehow navigate, right? When this guy, we don't know how to control it. Okay. Another clue, right, I want to bring to you is the idea of total variation. This actually has some meaning because we'll talk about quadratic variation soon. So the total variation of a path is very easy. It's like this, right? Suppose you have a path. Let's call it any function f of t, right, is a path. Because if I track, right, from 0 to t, for example, let's say this, right? So that's a path, right? Then the total variation of f from 0 to t is defined like this. Okay. The total variation of the path will be the absolute value of the change. This will be the total variation of the function on the time interval 0 to t. So, right, again, it's a strange mathematical object, but stay with me here. So what does it do, right? It basically, right, instead of, notice, if you were just adding the change, what will you get? If you don't have the absolute value, what are you getting? See if you understand all my calculus, yapping so far. If I were adding this without a change, what will I get? So without the absolute value, what will I get?
Is it fn minus f1?
Yes, ft minus f of 0. That's correct. This is exactly the integral, right? df. That's glorious formula again, right? So without the absolute value, thank you, Karim, right? Without absolute value, this makes sense for any process. Brown motion, I don't care how bad it gets, right? Because it's a telescoping sum. However, right, you will see that with absolute values start to show. Because now you start to accumulate all the change and you don't let the change cancel each other out. So in fact, right, you will see that if the process is very bad, its total variation will be, guess what? So for a regular process, right, the total variation of that thing on 0t is, let me see if you can guess. And for Brownian motion, the total variation of the Brownian motion is, can you guess these two objects? By regular, I hope you know what I mean, right? By regular, I mean like smooth, that kind of thing, not too bad.
Brown motion, is that 0?
Total variation cannot be 0, right? Why? Because you keep adding positive number. So you're thinking bad, but that's not that direction. It's the other one, which is it's infinity. is that strange, right? Can you believe that when you add this change and you push t to 0, somehow, but basically it's just moving so wildly that it accumulates so much change that it's actually infinity. This one you can verify on Python. I'll ask you to do that, all right? Of course, you won't get infinity on Python, right? But you get a very large number, so large. On the other hand, for a regular process, meaning the derivative exists, can you guess what the total variation must be? Look at this and guess what it will come out to be. Let me help you. What if the derivative is, what if this process always increasing? What if the derivative is always positive? If it's always increasing, then you don't need the absolute value, right? Then it's always this again. In other words, I hope it's convincing that it's the absolute value of the derivative. But the point is, this is going to be finite. In other words, for a well-behaved process, it must be finite variation. It's a definite number. It won't go above anything. But with bar motion, one clue that you can actually test, right, is that it's so bad is the total variation will blow up. All right, and it's even worse than that, but we'll talk about that later. All right. So okay, any question? I think there are people trying to get it. So any questions, let me know. All right, we'll continue on Thursday.